Hello everybody, and welcome to the last video on the binomial expansion for year 13 A-level for the Edexcel course. So we've done two lessons before. We've done the binomial expansion when the leading coefficient inside the bracket is 1. Lesson 2 we learnt how to deal with things if the leading coefficient was non-unitary. And right now we're going to put it all together and have a look at how we can use what we learnt before in the pure bit of the course this year on the binomial expansion to help us to find approximations to much trickier algebraic fractions. So because we're going to have a look at some stuff on partial fractions once again, in the warm-up questions I've included a couple to have a go at based on partial fractions. So the first couple are just doing the binomial expansion. The last two are, as I've said, about partial fractions. So try this warm-up, check the answers by watching the video after you've tried them. So pause now, try them, then press play to see if you've got them correct. And this warm-up will set you in good stead for the upcoming worked example and exercise. Okay, so I'm going to assume you've had a go at these now. So let's have a look together at the solution to warm-up question 1. So here for warm-up question 1, we have to show that the first three terms in ascending powers of x of the series expansion for f of x being 4 over 3x plus 5 cubed are these three here, which look quite horrible. We also need to state the range of validity of this particular expansion. So the first thing I'm going to do is just section off the question so I can write the answer with plenty of space. I'm going to rewrite f of x as a bracket with a negative power. So f of x, I can just rewrite it as 4 lots of 3x plus 5 to the power minus 3, because this bracket's on the bottom, so it's the same as to the power of a minus 3. So next up, we're best doing it so that the constant term is first and the variable x normally is second. So I'm just going to rewrite it as 5 plus 3x to the minus 3. Now, of course, this is like last lesson. We have a leading coefficient that isn't 1, so we need to factorize out the 5 from this bracket we need to find the binomial expansion for. So I'm going to put the bracket into bigger squared brackets, factorize out the 5, and divide both terms here by that 5. So 5 divided by 5 is 1, which is what we need. 3x divided by 5, we just write like so. So it's all of that to the power of minus 3. So we've got 4 times 5 to the minus 3 times 1 plus 3x over 5, again to the minus 3. Now this here we can calculate using, well, the calculator. So 4 times 5 to the minus 3, that just means 4 divided by 5 cubed. That's going to be 4 over 125. But again, don't take my word for it, always check these things with a calculator. So 4 times 5 to the power minus 3, 4 over 125. So this bit here, I'm just going to rewrite as 4 125ths, and then we can set to work on this expansion. So for binomial expansion, the first term, once the leading term in the bracket is 1, the first term again is 1. We then have the power the bracket's being raised to, in this case minus 3, and that's multiplied by the second term, 3x over 5. We only need to go up to the x squared term, so the next one is going to be the last one we need to do. So again, the power multiplied by the power minus 1 this time. So minus 3 minus another 1 is minus 4. That's two numbers, so divide it by 2 factorial. And then this thing here to the power 2, which is the same as how many numbers we have there. So that's what we've got thus far. So we can neaten this up. So we're going to have 4 lots. So 4 over 125. Now this here Minus 3 times 3/5, that's going to give us minus 9 over 5x. This here, minus 3 times minus 4 is 12. 12 over 2 is 6. This here, and again, check with the calculator if you want to. So it's 6 multiplied by 3 squared, which is 9, 5 squared over, which is 25. So it's 6 times 9 over 25. 6 times 9 is 54. So write this as plus 54 over 25 x squared. Finally, we can now expand this out. So 4 1/2 times 1 is obviously just 4 over 125. This next one, again, probably best using a calculator for that. So we're going to have 4 over 125 multiplied by minus 9 over 5. That gives us minus 36 over 625. So we have minus 36 over 625 lots of x, which is what we need to have. So it matches, which is good. And finally this one, 4 over 125 times 54 over 25. So I can leave that 4/25 as it is, and just multiply by 54 over 25, and we see that we get 216 over 3125, which is required. So that's our binomial approximation to f of x up to the x squared term at least. So we're almost done, but don't make the mistake of thinking you are done entirely, because there's this little thing here of trying to state the range of validity of the expansion. So here what we need to do is think, when is this expansion valid for? So the way we do this is we think about what actual bracket we applied the binomial expansion to, and it was this one here. So that's the actual binomial expansion part of the question. So we need the magnitude of whatever comes after the 1, this thing here, to be less than 1. So the range of validity, we need this 3x over 5 to have a size, a magnitude of less than 1. In other words, we need 3x over 5 to be no greater than 1 and no less than minus 1. If we now multiply both sides of this inequality by 5 and then divide through by 3, we're going to have minus 5/3 up to 5/3. And that's the range of validity. That's the range of values of x which will make this expansion valid and convergent towards the actual exact value of what f of x would be for any particular value of x within this range, of course. Let's now have a look at number 2. So, warm-up question 2. We need to find the percentage error in using that series expansion from question 1. So, if we estimated the value of f 0.1, what would the error be? So, give the answer to 3 significant figures. So, just reminding us from question 1 of what we had, that's what we have. So, f of x is this exactly, and f of x is this approximately. This is a binomial expansion of f of x approximated up to the x squared term. So first of all, we can work out exactly what f of 0.1 is. So f of 0.1, just plug in 0.1 into here for x. So f of 0.1 would just be 4 over 3x would be 0.3 plus 5 is 5.3. So f of 0.1 would be 4 over 5.3 cubed. Let's see what we get there. So 4 divided by 5.3 to the power 3 gives us this very long, awkward value here. So write down all the numbers on your calculator display for now. So it'd be 0.02686. What else was there? 781706. So this here is what f of x is. So f of 0.1 using this approximation, which is this here. These squiggly equal lines means approximately equal to. You should know this, but if not, that means approximately equal to. So f of 0.1 is about 4 over 125 minus 36 over 625 lots of x, where we're told that x is 0.1, plus 216 over 3125 0.1 squared. So all we're doing again is just subbing in the value of x as being 0.1. So if we just take the time to calculate this, it's a bit of a more awkward calculation, so let's just do this a bit more carefully. So we're going to have 4 over 125 to begin with, obviously, then minus 36 over 625 lots of 0.1, then plus 216 over 3125 lots of 0.1 squared. And if we hit equals, we get this value here, and we can get an exact answer of 0.0269312. So now we can work out the percentage error. So based off these two, percentage error, this goes back to GCSE really, it's the actual error divided by the exact value, which is this 0.02686781706 thing here, multiplied by 100. So just to work out on the top the difference between the actual and the approximation. So the difference is 0.0269312 minus the exact here, which is 0.0268, and so on and so on. Now this might seem like quite a bit to handle with your calculator, so I'm going to show you a slightly easier way, which means you're less likely to mispress on a value. So what I'm going to suggest is this value here is easier, okay? You can see that answer here. So let's just store that in our calculator memory. For example, A and S will come up. We've got that one stored. So the error on the top, I can just type answer minus 0.02686 781 706, all divided by 0.02686 781 706. Again, I'm not rounding at all here. I only ever really round at the very end to make sure I don't fall foul of any rounding error. So just make sure that's pressed in correctly. 2686 781 706, perfect. Now just multiply this by 100 to change it from a fractional error to a percentage error, and we see here that it's to three significant figures, 0.236%. So it's accurate roughly to 1 part in 500, so that's a very good approximation, only going up to the x squared term. So that's question 2 done. Question 3, we're asked here to express 3 over 9 minus x squared in partial fractions. This is a slight trick question because you're probably thinking, well, there's only one thing on the denominator. Well, this is a throwback really to GCSE work. What type of expression is 9 minus x squared. Okay, hopefully you're thinking, oh, it's a difference of 2 squares. If not, I've told you. So difference of 2 squares, this bit here on the bottom will factorise into 3 over 3 plus x, 3 minus x. And then, of course, I'll just highlight that's the same as this, difference of 2 squares. Then we split this into some value a we need to find over 3 plus x, plus another value we need to find b over 3 minus x. Now imagine multiplying this bit here, so we're just focusing now on this. Multiply through this fraction by both 3 plus x and 3 minus x, and obviously do the same on this side too. That would give us that 3 equals a. That 3 plus x times by that 3 plus x would cancel, so we'd have 3 minus x next to the a. And in a similar way, we'd have b brackets 3 plus x. We now need to pick our values of x tactically so that one of these brackets all vanishes, so we can just focus in on working out what one of the letters is. So what I'm going to suggest we might want to do here is pick x equals 3. So if x were equal to 3, if we sub this value in, the a bracket will vanish, so we can evaluate what b is. So when x is 3, the left-hand side is still 3. This a vanishes because 3 minus 3 is nothing. So we're going to have b times 3 plus 3, which is 6. So 3 equals 6b. Therefore, b equals 1/2. Next, we can pick x equals minus 3, because if x is minus 3, 3 plus minus 3 is 0, which would give us b times 0, so b would vanish, so we can just focus in on a. So that would give us 3 equals a times 3 minus 3, which is 6. So 3 equals 6a. Therefore, also a would be 3 over 6, which again is 1/2. So putting all this together, therefore 3 over 9 minus x squared is a, so it's 1 over 2 lots of 3 plus x. Plus 1 over 2 lots of 3 minus x. So the key there was spotting that we had to deal with a difference of 2 squares. Finally, now for our warm-up, let's finish off with the final question on the warm-up question 4. So again, it's a question about partial fractions. So express this as partial fractions. Now here we've got a repeated root, so it's 3 minus x all squared. So what we need to remember here is to write this repeated root twice, once to the power 1, once to the power 2. So we go a over 3 minus x to the power 1, which is just 3 minus x, plus b over 3 minus x squared, plus c over x plus 2. Now, in the same way, we just imagine this on both sides being multiplied by 3 minus x all squared and by x plus 2. On the left, therefore, we'd just be left with 3x minus 2, a over 3 minus x times by all of this. One of these 3 minus x's would cancel, but we'd still be multiplying by another 3 minus x. So we'd have a 3 minus x times this x plus 2. For b, 3 minus x all squared times by 3 minus x all squared, that would cancel with that. So we just have b times by x plus 2. And for C, over x plus 2 times x plus 2 would cancel, so we just have C multiplied by 3 minus x all squared. And again, what we're going to do here is just pick our values of x tactically so that we can eliminate the other two unknown letters and focus in and evaluate, work out the one we want. So it doesn't really matter which value of x we pick as long as some of these brackets are going to vanish. I would suggest though, looking at these two here, a and c, if we pick x equals 3, a and c would vanish, so we can work out b. So let's just pick, I would suggest in x equals 3. When x is 3, 3x is 9, 9 minus 2 is 7. So we're going to get for 7, the a bracket vanishes, 3 minus 3 is 0. C bracket vanishes 2, for the same reason. So we're just going to have b brackets 3 plus 2, which obviously is 5. Okay, so divide through by 5, we can see that therefore b has to be 7/5. We can now pick a different value. So looking here, we could pick x equals minus 2, for example. If we picked x equals minus 2, the a and b parts would vanish, so we can work out what c is. So let's have x being equal to minus 2 now. When x is equal to minus 2, 3 times minus 2 is minus 6, minus another 2 gives us minus 8. So minus 8 equals c. 3 minus minus 2 is 5. 5 squared is obviously 25. So divide both sides by 25. We can see that c must be minus 8 over 25. Final one to work out here is, obviously we've got b and c, we need to work out what a is. So if we now try a different value, now this is actually up to you what you want to pick. I tend to go for x equals 0 finally. It's just a habit of mine. When x equals 0, it's typically a fairly good value to pick. This just becomes minus 2. If x is nothing, we just have a times 3 times 2, which is 6a. b times 2 is 2b. And c times just 3 squared. 3 squared is 9, so that's going to give us 9c. But of course, we know what b and c are, so we can sub these in. So we have minus 2 equals 6a, whatever a might be, we're going to find it. b is 7/5, so 2 lots of b will be 14/5. c was minus 8/25, so times that by 9, that's going to give us minus 72 over 25. Rearrange. So on this side, I'm just going to have 6a left on its own. Over here, if I subtract 14/5 from both sides and then add on 72 over 25, I can find this value on the left. So minus 2 minus 14 over 5 plus 72 over 25. That gives us minus 48 over 25. Finally, divide both sides by this 6. You can see that a, therefore, must be, again, minus 8 over 25. And finally, piecing all this together, we've got our answer. So we know that a is that, we know that b is 7/5, and we worked out that c is this. So therefore, final answer coming up, we can say, so 3x minus 2 all over 3 minus x squared x plus 2, that equals a, which is minus 8 over 25, 3 minus x, plus b, so b is plus 7 over 5 lots of 3 minus x all squared, and c, so minus 8 over 25 lots of x plus 2. So sometimes the numbers you're trying to find with the partial fractions are awkward, so just because you get an awkward number, never assume that you're wrong. Go back and check it at the end of the exam if you can, but don't assume that the numbers are always going to be easy. So that's the warm-up done. Let's have a look at how we can use these partial fractions to help us when solving particularly awkward and nasty, long-winded binomial expansion type questions. So here, we're just going to get straight into a worked example, no frills, straight into just applying. So first we'll have f of x, which is this fairly awkward looking function here, defined for when x is not equal to minus 4, otherwise the denominator would blow up, and also defined for when x is not equal to 1.5, otherwise, again, the denominator would blow up because this bracket would be equal to 0. So first off, we need to find f of x in terms of partial fractions. So look at the denominator and look at the terms here. So we've got a repeated factor and a linear factor. So we say for f of x, we assume that f of x can be expressed in this following form. So a, some value to be found over x plus 4, plus b over 2x minus 3, plus c over 2x minus 3 squared. Again, for repeated factor, you'd have to do the repeated factor in ascending powers, starting from power 1 up to and including the actual power that the factor is raised to. So if that were factor 3, if that was cubed, it'd be that squared, and plus d over 2x minus 3 cubed. But I digress, we don't have to worry about this here. So now what we do is we multiply all of this by the denominator. So if I just were to rewrite this here, just for a second, get rid of this, and if I were to, for example, copy and paste what I just have here, bear with me a second, you'll see what I'm hopefully getting at. So we set this equal to that. So if I just multiply through both sides by x plus 4, 2x minus 3 all squared, then these denominators will all cancel and we'll have factors multiplying a, b and c. So we're going to have just this numerator left. So we'd have minus 2x squared plus 43x minus 38 equals a. So x plus 4 times by x plus 4, these two would cancel. That multiplied would cancel that denominator. So just have 2x minus 3 squared. b, because I'm dividing b by 2x minus 3, but then multiplying it by 2x minus 3 and another 2x minus 3, I'd get there another 2x minus 3, plus of course the x plus 4. And for c, which has been divided by 2x minus 3 all squared, then multiplied by this thing here, that would cancel. So next to c, we just have x plus 4. Now again, we just tactically think about what values of x we can pick, such that some of these factors will vanish, so we can just focus on working out one of these letters, a, b, or c. By the way, of course, we were told that x can't equal negative 4. That doesn't stop us from picking x equals negative 4, because all we're doing here is comparing coefficients. We're not actually using the function, we're just investigating to find what these constant terms here, a, b, and c, actually would be. So there's no harm in actually using x equals minus 4 or x equals 3 over 2 for just finding what a, b, and c are. It's a different process to actually inputting them into the function and trying to graph it. What we're doing here essentially is a very clever trick. So we can pick any value of x we wish. So what value of x should we pick? Well, what I'd suggest first of all is to actually go for x being equal to -4. That would knock out b and c, so we can focus in on a. So when x equals -4, what would that give us? When x equals -4, this over here will be -2 times -4 squared plus 43 lots of -4 minus 38. As I say, the b and c brackets will cancel, so we're just going to left with a 2 times -4 minus 3 squared. So let's calculate this and neaten it up. So we've got here -2 times -4 squared, let's put that in brackets, plus 43 lots of -4 minus 38. So what we've got here is -242. So -242. 2 times -4 is -8. Minus another 3 is -11. -11 squared comes out as +121. So we're going to have that -242 equals 121a. Then if we divide through by 121, we'll see that therefore a would have to be -2. So we've got one thing. The next thing we need to find is either b or c. So what could we pick for x next? Well, what we could pick next, if we picked x as being 3/2 or 1.5, whichever you prefer to think about it, a and b would vanish and we can then focus on working out c. So next I'm going to pick that x is 3/2 and see what we get from that. So when x is 3/2, this here will become -2 lots of 3/2 squared plus 43 lots of 3/2 minus 38. That will equal just c times 3/2 plus 4. So if we neaten this up, we can work out what it has to be. So be careful when putting this on a calculator, because this is fairly awkward. So -2 and brackets 3/2 squared plus 43 lots of 3/2 minus 38. So that's going to give us 22. So 22 equals, that's 1.5 plus 4. 1.5 plus 4 is 5.5. That's 5.5 lots of c. Divide through by 5.5, we see that c would have to be equal to 4. So c is 4. So even though these numbers are awkward, a, b and c could come out as being nice whole numbers, whereas as just one of a warm-up, we could actually have like something easy to input, but then a, b and c could come out being something quite awkward and fractional. So you just never know with these questions. So keep an open mind. Don't necessarily think you've made a mistake if you've got something fractional. So we've got a and c next. So next what I'm going to suggest is we can just go for x equals 0. We know a and c. We can work out b by just subbing in anything for x. Typically x equals 0 is an easy thing because it eliminates lots of different awkward bits and pieces. So if x is 0, this just becomes minus 38. If x is 0, we have a times minus 3 squared. Minus 3 times minus 3 is 9, so we get 9a. When x is 0, we get b times minus 3 times positive 4. So that's going to be minus 12 lots of B. So we can fill this one in. So that's minus 12 lots of B. And when x is 0, C times 4 is just 4C. But of course we know what A and C actually are, so let's input those. So minus 38. A is minus 2, so 9 times minus 2 is minus 18. Then we have minus 12B, which we just leave as it is, because you don't know what B is yet. And C was 4, so 4 lots of C is going to be 16. If we rearrange this next, so if I add 18 to both sides and then minus 16 from both sides, we can see what minus 12B is. So we're going to have minus 38 plus that 18 minus off that 16, we get minus 36. So minus 36 equals minus 12B. Therefore, if we divide through by minus 12, B is minus 36 divided by minus 12. So B comes out as being positive 3. So the final step, conclude what f of x is as partial fractions. So therefore, f of x can be expressed as A, which is minus 2, over x plus 4, plus B, so plus 3, over 2x minus 3, and C is 4, so finally plus 4 over 2x minus 3 all squared. So that's what f of x is expressed as partial fractions. Part B, it says, hence or otherwise find the series expansion of f of x up to and including the term in x squared, simplifying each term. So let's just remind ourselves what we had from part A. So from part A, we worked out that f of x was as follows. So you might be thinking, why have I colour-coded it like so? It's because we've got 3 different linear factors on the bottom. Sorry, not 3 linear factors. We've got 2 linear factors on the denominator and 1 here. So we're going to actually have to do 3 binomial expansions. So because we've got 3 different binomial expansions, I'm going to do these in different colours: red, blue, green. So first of all, let's just focus in on minus 2 over x plus 4. So minus 2 over x plus 4. I can rewrite this one as minus 2 brackets x plus 4 to the minus 1. Now, what I'm going to suggest we do as well is to have the constant term written first. So if I just write this as minus 2, put the 4 first, that's 4 plus x to the minus 1. Now, like I mentioned before, we can only do the binomial expansion when the leading term is unitary. That 4 is not 1. We need to make it a 1. So, right, minus 2. Now I'm going to factorise out this 4. So divide the 4 and the x by 4. 4 over 4 is 1. X becomes x over 4. So this thing here is all to the power minus 1. So that's going to give us minus 2 times 4 to the minus 1 times 1 plus x over 4 to the minus 1. So now we can set about working out what this is actually going to be. So minus 2 times 4 to the minus 1. Again, if in doubt, calculate it. So minus 2 times 4 to the power minus 1. It'll give you negative half. So we have minus a half. And we can do the binomial expansion on this now. So the first term is going to be 1. Then plus the power multiplied by this thing here. So plus minus 1 times x over 4, then minus 1 times minus 2, all over 2 factorial, multiplied by this thing here, squared. Now we can expand this out to work out what this thing would be. So minus a half times 1, that gives us minus a half. Minus 1 times x over 4 is negative a quarter x. Negative a quarter x times minus a half will actually give us positive x over 8. And this one here, I'm just going to use a calculator for, because this looks a bit nasty really. So I'm going to multiply through by minus a half. So we're going to have minus 1/2 multiplied by minus 1 times minus 2, all over 2 factorial. That just means 2 times 1, which is 2. And we're multiplying that by x over 4 squared. So I'm going to multiply that by a quarter squared to find the coefficient of x. We get negative 1 over 32. So we're going to have minus 1 over 32 x squared. So essentially just minus x squared over 32. So that's one of them done. Next, we need to think about 3 over 2x minus 3. So same idea. I'm going to write this as 3 lots of 2x minus 3 to the power minus 1. Once again, my suggestion would be to have the leading term first. So have the constant term first, I mean to say. So 3 lots of minus 3 plus 2x to the power minus 1. Again, we need to factorise out this so that it starts with a positive 1. So I'm going to say it's 3. Factorise out this minus 3. Basically divide both these terms here by negative 3. Negative 3 divided by itself gives us the 1 we need. This divided by negative 3 gives us minus 2x over 3. So we have all of that to the power of negative 1. So we've got 3 times minus 3 to the minus 1 multiplied by 1 minus 2x over 3 to the power minus 1. So 3 times minus 3 to the power negative 1. Again, let's do this on a calculator just so we know what we're doing. So 3 times minus 3 to the power minus 1. That's going to give us negative 1. Now we do the binomial expansion, only up to the x squared term again for this here. So the first term, as ever, always is for 1, then plus the power minus 1 multiplied by this thing here, which, be careful, is minus 2x over 3. Be very careful about negatives. Then plus minus 1 times minus 2 divided by 2 factorial, all over minus 2x over 3 squared. So again, expand out and neaten up. So minus 1 times 1 gives us minus 1. Minus 1 times minus 2/3 gives us positive 2/3. Positive 2/3 times minus 1 again gets us back to minus 2x over 3. And this one here, that's a calculator job, methinks. Give him to move this calculator out of the way. So we're going to have minus 1 there, times by minus 1 times minus 2 all over 2 factorial, which is just 2. This fraction here is minus 2/3, so I'm going to times that by minus 2/3 all squared. Put it in brackets. Oops. There we go, finally right. Minus 2/3 squared. We get minus 4/9. So we're going to have minus 4/9 x squared. And finally, this bit here, the green, we do the same again. So again, this can take a while. Good news for you watching at home is that actually these questions can be in excess of 10 marks if they are asked, just to reflect how long-winded they can be. So 4 over 2x minus 3 all squared, we write first of all as 4 lots of 2x minus 3 to the minus 2. And again, in the same way, write the constant term first. So that's the same as 4 lots minus 3 plus 2x to the minus 2. So we've got the 4. And again, because it's the same bracket, the power's different, we can use what we had here to help us. So again, we factorise out the minus 3. So it's going to be exactly the same thing here, just that's going to be a negative 2. So we've got 4 lots now, minus 3, 1 minus 2x over 3, to the power negative 2. So that's going to give us 4 times minus 3 to the minus 2, multiplied by 1 minus 2x over 3, to the power minus 2. So again, on the calculator, work out what 4 times minus 3 to the power minus 2 is. That would be 1 over 3 squared, which is 9. So 4 times 1 over 9 is going to give us 4/9. So we have 4/9. Now we do a binomial expansion on this one, up to the x squared term. First term again, as ever, is 1. Then the power multiplied by this. So we have minus 2 multiplied by minus 2x over 3. Then the power times by the power minus 1, all over 2 factorial, times by this thing here, squared. Finally, expand out and neaten up. So 4/9 times 1 is obviously just 4/9. This one here, minus 2 times minus 2/3 gives us positive 4/3. 4/3 times 4 over 9. Trying to calculate, I don't believe it's going to give you 16 over 27. So I have 16x over 27. And this final one, again, is going to be a calculator thing. So we've got 4/9 on the outside, there. We're going to multiply that by minus 2 times minus 3, all over 2 factorial, which is just 2, multiplied by this fraction here, minus 2/3 squared. And that drops out as 16 over 27, again weirdly. So that's 16 over 27 x squared. So now we've got all the ingredients to actually answer this question. So we can actually start by saying what f of x actually is in terms of this expansion. So therefore, f of x is approximately equal to these bits here. So the constant term, we can just look at these bits here. So the constant term, we've got minus 1/2 there, minus 1, and 4/9. So let's combine those into 1. So we've got here minus a half, so I'm going to just call that minus 0.5 for simplicity, minus another 1, and plus 4/9. So we've got minus 19 over 18. So the first thing is we've got minus 19 over 18. Then looking at the terms involving x. So we've got 1/8 of an x there, minus 2/3 of an x here, plus 16 over 27 of an x there. So combine these. So hidden behind the calculator was 1/8 of an x. So 1/8 minus 2/3 plus 16 over 27. That gives us positive 11 over 216. So we've got plus 11 over 216x. Whoops, that isn't what I wanted to do. That's a different sort of pen. And finally, the terms involving x squared. So involving x squared, we've got minus 1/32 minus 4/9 plus 16 over 27. So combine all these into one. So behind the calculator was minus 1 over 32. Oops. Then minus another 4 over 9. And plus 16 over 27. That gives us 101 over 864. So the final one is plus 101 over 864 lots of x squared. Very awkward looking approximation. But sometimes, you know, you might have something quite awkward to work out. So nature of the beast. So that's our binomial approximation to f of x. Whew. And we're not even done with this worked example. I've made it particularly meaty as a real stretching challenge. Let's have a look now at part C of this worked example. So first of all, we need to now think about stating the range of values of x for which this expansion is valid. So what we need to do here is just consider what expansions were actually performed, what the brackets were which were actually expanded. So just going back to a part of the question. These are the actual brackets we were dealing with. Okay, so we had 1 plus x over 4 to the minus 1. So based off this one here, we did the binomial expansion on this bracket, you see. We need the size of this thing here to be less than 1. So in other words, multiply both sides by 4. We need x to be less than 4. These two here are both minus 2x over 3. So for both these ones here, we just need the size of minus 2x over 3, which is the same as the magnitude of 2x over 3, to be less than 1. Times by 3, divide by 2, means we want the size of x to be less than 3 over 2. So what satisfies both of these? What range satisfies where the size of x is less than 4 and also the size of something is less than 1.5? We've got to go for this one. For example, 2.5 would satisfy this one, but it wouldn't satisfy this one. The only range which satisfies both is x being in between minus 1.5 and 1.5. So therefore, we need x to be in between minus 3 over 2 all the way up to and not including 3 over 2. That's our range which makes the expansion valid. Lastly, part D, we need to find the percentage error in using this series expansion from part B if we estimated the value of f of 0.02 and give that answer to 3 significant figures. So just reminding ourselves of what we actually had for our binomial expansion for this, it's this here. So that's it exactly. This is our approximation. So what we need to do here into both bits is pop in the value of 0.02 for x. So f of 0.02 into this thing here. Again, it's just an awkward job to do. So let's work out what we have. So it's going to be -2. Just type it exactly as it appears. So -2 lots of 0.02 squared plus 43 lots of 0.02 minus 38, all of which divided by 4.02, then 2 times 0.2, sorry, 0.02 minus 3 squared. You should get minus 1.054488333. Whereas our binomial expansion approximation we get f of 0.02 is roughly, well, let's see. So we're just going to pop in 0.02 into this. So we're going to have minus 19 over 18 plus 11 over 216 lots of 0.02 plus 101 over 864 lots of 0.02 all squared. And for that we get minus 1.05449 0.278. So as you can see already, these are very close to one another. So the difference between these, in other words the error, is going to be the size difference between these two. So it's going to be negligible. As you can see, it's accurate up to 4 decimal places. To 4 decimal places, it'd be minus 1.0545, the same for this one. So on the calculator, we've got stored in this value here for our approximation. If I then subtract from that the actual, so minus this, in other words, if I just add on this one here, we'll find the difference between them, in other words, the error. So 4488333, oops, one too many threes. It's just absolutely minuscule. So it's minus, well, the actual size of difference is 1.944. And that's, I believe, 5 sevens. I never round until the very last step. 1, 2, 3, 4, 5 times 10 to the minus 6. I'm going to discuss with you why the approximation is just so amazingly accurate in a moment. So if the error is 1.94ish times 10 to the minus 6. So therefore the percentage error is going to be this actual error, which is 1.9941234 5 divided by the actual exact answer, which is this, multiplied by 100. But because it's a percentage error, which has to be a positive value, we could actually just interpret this as just the size of this, because this is going to come out as a negative because of this negative at the bottom. So what we could do here is just scrap that, knowing that a percentage error only makes sense when you have a positive percentage. So using what's stored on the calculator, we've got the actual difference, okay? So I'm just going to times that by -1 to make it nice and positive. Then I'm going to divide that by the actual, well, the size of the actual. So 1.054488333 times by 100. We get that. So it's times 10 to the -4. Look, I need to give this to 3 significant figures. So to 3 significant figures, I keep the 1, the 8, and the 4. So I'm going to give it as a normal number, as an ordinary number. So it's times 10 to the -4. That's going to be 1, 2, 3, 4 zeros, followed by 184. And that's our very tiny percentage error, so it's an excellent approximation. Why is the approximation so accurate? Well, it's because about this range of validity. If x is much smaller than the range of validity, then the approximation is much better. As you approach the limit of the range of validity, it is not as good an approximation. And of course, when you go beyond the range of validity, the approximation isn't valid at all. So the best approximation is when the magnitude of x is much smaller in terms of relative size than the limits of the range of validity. So 0.02 is tiny. 0.01 would give an even better approximation. So that's just a bit of colour commentary for you there. So an absolute beast of a worked example. If you can do that and follow that, you can do them all. But don't take my word for it, practice these. So these are the ones I want you to have a go at. Turn to page 102, 103, exercise 4C in the lovely blue Year 13 book. Try question 1 and question 4. Question 6 and 7 in particular are very similar to what you might encounter in an exam situation. If these come up and you know how to do them, you're absolutely quids in. They might take a long time to do, but the actual mental power isn't too bad. It just takes a lot of work, but it's not actually that mentally taxing once you've practiced enough on them. So good luck practicing. Please do subscribe and comment in the comment section. I do enjoy reading them. Take care and tune in soon. So from me, bye for now.